Thanks everyone for listening in today. I want to talk about tuning machine learning models, focusing on hyperparameter tuning, but it will be very relevant for those interested in speeding up performance, where hyperparameter tuning is often very computationally expensive, and also in terms of course, tuning the accuracy or metrics around models. This is also critical. So just quickly about where I'm coming from. I spent most of my time at Databricks as a software engineer working on ML and advanced analytics, and am now a solutions architect. One requisite slide about the company, Databricks is proud to have been fundamental in building out these important open source projects, Apache Spark, Delta Lake, and MLflow. Cool, so to get into it, I want to spend 2 minutes quickly going over what hyperparameters are. If you're not familiar with the material, hopefully this will help. If you are, I think it will be nice in terms of setting some perspectives. Cool, so I'm going to be using later a demo looking at Fashion MNIST, which has a bunch of images of clothing. So let's take a look at this one. It looks like a shoe. My first model that I fit said, this is a dress. Probably not correct. The next model I fit said, this is a sneaker. And that's actually pretty accurate. And what's the difference here? Well, Model 2 actually had better hyperparameter settings, the learning rate, model structure, and so forth. So stepping back, what is a hyperparameter? Well, the statistical sort of definition or perspective, which I'd like to give, is assumptions you make about your model or data to make learning easier. From a practical perspective, this is inputs your ML library does not learn from data. There are a bunch of parameters in a model which the library does learn from data, but it also takes manual inputs. And I'll call those hyperparameters because they're knobs which can be tweaked. Some of these I would call algorithmic. These are more sort of problem-dependent configs which may affect, say, computational performance or speed, but might not really be super related to the statistics or modeling perspective. Cool, so how do we tune these? Well, there's sort of three perspectives I'll give, matching those from before. If you're a statistician or application, domain expert, you might bring knowledge which lets you set some of these settings a priori. Looking at sort of that practical perspective, there's an ML library, it takes some inputs, it gives an output model which can be tested, and we can optimize it like a black box. This is a pretty common way to do tuning and quite effective if you do it effectively. And the final way is to basically ignore until needed. And I think this is a common approach I take with some of the more algorithmic aspects. If a config really only affects the speed of learning, then I may not bother tweaking it until needed. Cool. So I'm not going to cover in this talk statistical best practices or overview different methods for tuning. And that's because there were talks at Spark and AI Summit last year covering some of these. I'll give references at the end. In this talk, I want to focus on data science sort of architecture and workflow best practices and tips around the big data and cloud computing space. Cool, so hyperparameter tuning, of course, is difficult, else I wouldn't bother giving a talk on it. And I want to outline a few reasons why. The first is that these settings are often unintuitive. If you've taken an intro to ML class, the first hyperparameter you probably touched on was regularization. This sort of is intuitive, avoiding overfitting, limiting model complexity. But if you take any given application, it's really hard to say a priori how you should set regularization. And, of course, let's not even get into neural net structure. The next challenge is that this involves non-convex optimization. Here, I took an example problem where on the x-axis is learning rate, and on the y-axis is test accuracy. And you can see it jumps all over the place. Well, this is a bit contrived in that a lot of this stochasticity is from the optimization process itself, some randomization there. But it kind of drives home the point that this isn't a nice simple curve you can use traditional optimization methods on. You really need some specialized techniques. And the final element is cursive dimensionality. Since this is a non-convex problem, then as we increase the number of hyperparameters, here plotted for an example problem on the x-axis with 7 possible settings for each hyperparameter, we can see that the fraction of coverage of the hyperparameter space for a given budget of, say, 100 hyperparameter settings drops exponentially as we go to the right. And so by the time we hit maybe 3 hyperparameters, we can cover, about a third of the space. And after that, we can hardly test any of the actual settings for hyperparameters. And this leads, of course, to high computational cost if you try to push this coverage up. So given these challenges, I want to step back and see how we can address them. Now, I won't be able to give, neat solutions for all of them, but I do want to talk about useful architecture, patterns, and workflows, and a sort of a bag of tips at the end. So starting off with architectural patterns. At a high level, a lot of this boils down to single machine versus distributed training. And I'll break it into 3 workflows, which 99% of the customers I've seen in the field fall into, or use cases fall into. Single machine training, distributed training, and training one model per group, where a group might be a customer or a product or what have you. So looking at the first one, single machine training is often the simplest, involving these or other popular libraries where you can fit your data and train a model on a single machine. Now, in this case, if I'm doing it on my laptop, I'll just take, say, scikit-learn, wrap it in tuning. That tuning could either be scikit-learn's tuning algorithms or another method, and run it. But if I want to scale it out via distributed computing, it's also pretty simple, where I can train one model per Spark task, like in this diagram, where the driver isn't doing much, but each of the workers is running Spark tasks where each one is fitting one model and one possible set of hyperparameters. And I wrap the entire thing in a tuning workflow. This allows pretty simple scaling out and is implemented in a number of tools. So Hyperopt, which I'm going to demo later, has a Spark integration we built, allowing the driver to sort of do this coordination across workers. The ML team I'm from also built a Joblib integration with a Spark backend, which can power scikit-learn's native tuning algorithms. And then finally, this can be done manually via pandas UDFs and Spark. The next kind of paradigm is around distributed training. And there, if your data or model or combination thereof are too large to train on one machine, you may need to use Spark ML, Horovod, XGBoost, or something which can train a model using a full cluster. If you do want to scale this out further, then rather than training one model at a time, you can train multiple ones in parallel. And so that might look something like this, where you wrap the training process, which is orchestrated from the driver, say by Spark ML, with tuning. And the possible tools which come into play here are, for example, Apache Spark ML, which has its own tuning algorithms. And those actually do support a parallelism parameter, allowing you to fit multiple models in parallel to scale out further. You can also note that from the driver's perspective, you can actually use any sort of black box tuning algorithm or library such as Hyperopt, because it can make calls from the driver and never really need to know that these calls are using a full Spark cluster. The final kind of paradigm is training one model per group. And here the interesting case is where there are enough groups that we really get back to that single machine training case, where we can scale out by distributing over groups and train each group's model per Spark task. So here's kind of a diagram of it. And in this, I'm recommending using Spark to distribute over groups within each Spark task, doing tuning for a model for that group. You can do tuning jointly over groups if it makes sense, though. Important tools to know about here are, of course, Apache Spark and Pandas UDFs, or UDAFs, to do this aggregation and coordination. And within each worker, you could use scikit-learn's native tuning, Hyperopt, or whatever. Cool, so that touches on the main architectural patterns I've seen in the field. And getting into workflows, I'd really like to touch on common workflows and particular tips for each. So in order to get started, my first piece of advice is start small. Bias towards smaller models, fewer iterations, and so forth. This is partly being lazy, small is cheaper, and it may suffice, but it also gives a baseline. And some libraries, such as, say, TF-Keras, which I'll demo later, support early stopping algorithms, which can take that baseline into account. It's also important to think before you tune. And really by this, I mean a collection of kind of good practices. So make sure you observe good data science hygiene, separate your training, validation, and test sets. Also, use early stopping or smart tuning wherever possible. I often see people use, say, uh, Keras, where they are tuning the number of epochs, but it's often better practice to fix the number of epochs at a large setting and use early stopping to stop adaptively to be more efficient. Also, pick your hyperparameters carefully. Now, this is pretty vague, but I'll give at least an example. Sort of a common mistake I've seen made with MLlib tree models. They have two parameters, hyperparameters, which are important for controlling the depth or size of the tree, max depth and min instances per node. These serve somewhat overlapping functions, and I've seen them tuned jointly, but it's often better to fix one and tune the other, depending on what you're going for. Finally, I'll mention picking ranges carefully. This is hard to do a priori, but I think speaks to the need for tracking carefully during initial tuning and improving that later on. The next set of workflows I'll talk through are models versus pipelines. So for this, one important best practice is to set up the full pipeline before tuning. And the key question to ask there is, at what point does your pipeline compute the metric which you actually care about? Because that's really the metric that you should tune on. Related to that is, whether you should wrap tuning around a single model or around the entire pipeline. And my advice there is to generally go bigger. That's because, featureization is really critical to getting good results in ML. I had a professor in computer science or for an AI course back in early 2000s make the joke that, if you had the best features possible, then ML would be easy. For example, if one of your feature columns were the label you're trying to predict, you'd be done. And of course, that's facetious, but it does get to the good point that taking time to do featureization, and in particular tune it, is pretty critical. So optimizing tuning for pipelines can come into play when you start wrapping tuning around the entire pipeline. And my main advice there is to take care to cache intermediate results when needed. The final set of workflows is really around evaluating and iterating efficiently. And there I'll say validation, data, and metrics are critical to take advantage of. And just a priori, record as many metrics as you can think of on both training and validation data, because they're often useful later. Tuning hyperparameters independently versus jointly is a pretty interesting question where, since you do have this cursive dimensionality, it is tempting to say, well, let me tune one hyperparameter, fix it at a good value, then the next, then the next. That's sort of more efficient, but some of those hyperparameters depend on each other. And so smarter hyperparameter search algorithms, like in Hyperopt, which we'll demo later, can sort of take advantage of that and be pretty efficient. And the final thing is around tracking and reproducibility. Along the way of producing all of these models and tuning, you generate a lot of data, code, params, metrics, etc. And taking time to record these, as well as using a good tool like MLflow to record them, can save a lot of time and grief later. One tip is to parameterize code to facilitate tracking. That way, as you're tweaking what you're running, you're not tweaking complex code, you're tweaking simple inputs to that code. Cool, so I'd really like to demo this. So I'll switch over to a Databricks notebook. Cool, so here I am in a Databricks notebook. Keep in mind this code and the tools I'll be using are open source, so could run in whatever venue. And in this, I'm gonna demo scaling up a single machine ML workflow. The goal being to show some of the best practices, which we had talked through in the slides. I'll be working with Fashion MNIST, classifying images of clothing using TensorFlow.keras. And the tuning tool I'll use is Hyperopt. This is open source, provides black box hyperparameter tuning for any Python ML library, has smart adaptive search algorithms, and it also has this Spark integration for distributing and scaling out, which my team contributed a while back. Cool, so I'm gonna skip through some of this initial code for loading the data. There are 60K images in training, 10K in test. Labels are integers 0 through 9 corresponding to different clothing items. Just to get a sense, here are the types of images we had seen from the slides earlier. Here's our sneaker, not a dress. And so I pulled a open source example from the TensorFlow website and looked at it for what hyperparameters I might tweak. Well, model.fit had a few interesting ones. Batch size and epochs jumped out at me. Of course, for epochs, I'm going to use early stopping instead, and that way I don't have to bother tuning it. The optimizer atom takes a learning rate, which I'll tweak, and the model structure, for that, I picked 3 example structures, small, medium, and large in terms of size and complexity. There are others which are future work. So taking a look at tuning these, I'm not going to go through the code in detail, but I do want to highlight the beginning where I've taken care to parameterize this workflow. In this way, as I tweak batch size, learning rate, and model structure, I can just pass those in as parameters rather than changing my code itself. I'm going to skip through most of this code. I will note that I'm taking care to log things with MLflow at the end. And note that I can run this training code with some parameters. This is just an example run. So now I'll skip down to tuning with Hyperopt. So my search space here is going to be specified using the Hyperopt API. If you're not familiar with it, don't worry about it. Here I'm saying there are 3 hyperparameters I want to tweak, and each is sort of given a range and a prior over that range where I want to search. And here's a good example of taking care of choosing those ranges carefully. Here I'll call out that I used log uniform distribution for the prior for learning rate to bias towards smaller learning rates because I've seen success with those in the past. And then I call Hyperopt's minimize function where I minimize the loss of this returned by this training code over a search space using a smart search algorithm. Here's the Spark backend saying let's fit at most 8 models, testing possible hyperparameter settings in parallel at a time. 64 possible models total, and run it. So I already ran this because on this toy cluster, which had 2 workers, no GPUs, it took about an hour. Good example of why it's important to make sure you record beforehand the metrics you really care about. It's also nice to take a look at those metrics, of course. And here I'm using the MLflow experiment data source where I'm loading the runs for the experiment for this notebook. Adding a column duration. And we can take a look at this. Here's a histogram of the duration of tuning models. Most ran pretty quickly, but a few took the better part of an hour. And so, might want to consider whether we want to spend that time. Well, so I'm going to open up the MLflow UI for this notebooks experiment. And here we see I have this one run for Hyperopt with a bunch of child runs for each of the models we fit under the hood for different batch sizes, learning rates, and model structures, different metrics, and also, of course, the model artifact. In the MLflow UI, I'm going to compare these. I've already set this up. And it's pretty interesting to kind of take a step back and look at the correlations between batch size, learning rate, and model structure with our loss. If we look at some of the best losses, we can see those came from this medium model structure, small learning rates, and so forth. But if we increase this, we can see pretty good losses actually came from that largest model structure. But what's interesting is when we look at actually the loss or metric that we really care about, the test accuracy. And there, if we look at the best possible model, it actually had kind of a middling loss. and was from this largest model structure. So it really speaks to the need to kind of take time to record extra metrics, and especially the ones you really care about. And so that you can go back later and maybe explore this model structure further. Cool, so I'm gonna flip back to the slides. Cool, so that was a demo to give you a bit of a taste of what we've been talking about in architecture and workflows. I'm gonna go quickly through these last slides because they're really a grab bag of tips and details and largely have quite a few references for um, looking at later on. So as far as handling code, getting code to workers is an interesting problem where it's generally simple, use pandas UDFs or integrations, but debugging problems can be tricky. And there my main recommendations are to look in worker logs and in Python, import libraries with enclosures. Passing configs and credentials is also can be tricky. Here I didn't show it because Databricks is handling the MLflow runs and credentials under the hood. But this helpful resource has some info on some of these topics. Moving data is also an interesting problem where for single machine ML, broadcasting that data or loading from blob storage can both be good options depending on the data size. Caching data can also come into play and becomes even more important in distributed ML. Blob storage data prep is really important as data sizes start to grow, and their Delta Lake, Petastorm, and TF records are key tech to be aware of. And these links to resources are nice in terms of walkthroughs of these different options. Then finally, for configuring clusters, here are the main discussion points. Not tips really, but discussion points around single machine ML, where sharing machine resources and selecting machine types can be pretty important. For sharing resources, they're really talking about the question of if you have multiple Spark tasks fitting different models on the same worker machine, how are they sharing resources? So thinking about that beforehand can be critical. For distributed ML, right-sizing clusters and sharing clusters can be important topics. And for the latter, I'd really say take advantage of the cloud model and spin up resources as needed so that you don't need to share clusters and complicate things. And again, this resource has a bit more info. Cool, so to get started, I'd recommend first taking a look at the different technologies which you've been working with. Tools to know about here are listed on the right for each of the technologies on the left. I won't go through these, but definitely take a look at them if any of these techs call out to you. And finally, the slides and notebook are in tiny URLs up there in the upper right, and those slides will have the links to these many resources I've listed. There are a few more listed here, and yeah, I hope they're useful, including those talks from last year, which go into a bit more of the fundamentals of hyperparameter tuning. With that, I'd like to say thank you very much for listening and love to answer a few questions.